Welcome back. We're looking at adding vectors now. Subtracting vectors won't be too different, so I'll just kind of mention it after the fact. But if we look at the example, a plane set on a bearing of north 60 degrees east with a speed of 350 kilometers per hour is affected by a tailwind of 50 kilometers per hour from the south. Determine the resultant velocity. So first thing to point out, just that the term resultant implies the basically what is the result of the rest of the situation. So in this case, we have the initial flight path of the plane being 300 kilometers, 350 kilometers per hour, north 60 east. So if you remember, or in case you didn't catch it, when we see something like north 60 east, it means starting from the north, heading 60 degrees towards the east. So this is the situation we're looking at right now. The plane is from the north, headed 60 degrees towards the east. So this is sort of this angle in here. The tailwind is coming from the south. Now what's going to happen if you can sort of picture it, if I have a plane, this is a very rudimentary plane, kind of flying along, intending to go, that was not intended, intending to go along this path, and the tailwind comes along and pushes it, it's going to be pushing it up this way somehow. So instead of being able to follow the path that it wants to follow, with the extra push behind, it's going to kind of go something like this. So what we do in order to kind of figure out the resultant here is we actually add the two vectors together. And to add vectors together, we always place them head to tail. So the head of this one, the tip of this one, touches the tail of the other one, the back end of that one. The resulting value is going to be the vector that comes in right here. Sort of starts at the tail of the one and ends up at the head of the other. It's as if two things have happened. So you can sort of think of it as we started down here, we went this path, and then we went this path. Of course, it's not exactly what happened. The plane didn't fly to this spot and then change directions entirely, but it actually followed the new path that I'm trying to create. This one right here. But the reason it followed that path was because of the two other pieces, the two other vectors kind of combining to give us this path. So I'll make that red. And the question really is asking me what is the size of this, knowing that the 50 is over here, and what is the direction of it. So sort of in the same way that we described the direction of the 350 as being north 60 towards the east, we'll have to figure out what the direction is from the north towards the east of the resultant path. That'll be kind of the last step. So if I look at these the two values I've got, I'm essentially just missing one piece of information in here. If I have two sides of a triangle, I can find the third as long as I know at least one angle. So something in the information that I have here has to help me get to this point. And so it's a little tricky, but if we sort of think about just extending this line, I'll extend it with a dotted line instead. Take that out. I'm just sort of looking at the northeast, southwest sort of ideas. 60 degrees was my angle between the north and the path that we were actually taking. And so when we get up to this point up here, the 60 degrees, the 60 degrees that's in here is also going to be right up in here. It's a Z angle situation. The other way to think of it is if I did extend these dotted lines that are meant to indicate north, south, east, west, then with 60 degrees being taken up out here, I must have 30 degrees up in here. Okay, so somehow we have to kind of put together the fact that the 60 is not part of the triangle that I'm working with, but that it does help me establish another 60 over here, or again, if we just sort of think about extending these imaginary lines for east, south, north, east, west, north, and south, then this angle in here must be 30. And of course, this angle up here is going to be 90. So the trickiest part of these types of questions will be figuring out the angle that we have when it's not actually given to us. Now, once I have that, some of these extra lines, and even this extra angle, I guess, I've essentially got 120 degrees in here, 50 up here, and 350 down here. And so my diagram, just in simplest form, looks something like this, with a 120 degree in there, a 50, and a 350. And I'm looking to find this as my first step. And so this is a cosine law. So if you remember, we have c squared equals a squared plus b squared minus 2ab cos of the angle that I'm dealing with, which we have been traditionally calling cos of c, just so that we remember that this side is opposite the angle that we're dealing with. Okay, I'm going to pause the video, finish up the question. Okay, so finishing up here, A, B, 50 and 350 respectively. Again, whichever order doesn't make a difference. Cosine of 120 is the angle that the 120 is the angle we're looking for, so cosine of 120. And when we work it out, we find that C is approximately 377.5 kilometers per hour. So that's the speed that we're traveling. What we're also interested in is the direction. And so when I look at this triangle, I can find the missing angle based on the fact that I now know this is 377.5. I now have a simple, straightforward sine law type formula or type situation. That's not great. And so I'll just kill this, I guess. Sine of theta over the 50 is equal to sine of 120 over the 377.5. Rearrange and we find that the angle in there, the theta value, is 6.6. And so that's essentially the part that's taken away from the 60. So the 60 was sort of that full angle back to the 350 degree, the actual intended path of the flight. And then we take off the 6.6 degrees for the actual flight path and find that we are now traveling 377.5 kilometers per hour on a bearing of north 53.4 degrees east. So again, off by 6.6 degrees from the intended path. As far as subtraction goes, sort of a real quick comment. We know that addition and subtraction are essentially opposites of one another. Going way back, if you had something like 5 minus 4 and 5 plus negative 4, I'm subtracting the positive or adding the negative. I'm doing the opposite mathematical operation to the opposite number, and I get the same result. The same is going to be true for subtracting vectors. Essentially, instead of adding the existing vector, we get the opposite vector and add it instead. So subtract, if it said subtract the 50, for example, we would have to add the essentially negative 50. So I'm going to clone that page super quickly and just, okay, so if we just had a simple subtraction here, okay, I'll pause this one more time.